She graded it.
I know. It's irrational. It's because I feel like I did miss some. The word like pie is irrational. Like if it's rational,
And then our
find the common number by both the numerator and the denominator. What can I do anytime in the same
she's another person.
Yeah. Oh, you just didn't sign it. Okay.
I didn't, but I did.
Maybe on the wrong one. Oh, yeah.
How many ways can I write the number one in the question?
I don't really like to have
I know what number. 4.
Fraction by into the lowest term, right? Can you simplify a fraction into the lowest term?
Well, folks, it sounds like the volume went down a little bit. So let's go ahead and discuss these. When we use the words rational and irrational in common society, what do we mean? So when on a day-to-day basis, if we refer to something as rational or irrational, what is that actually? What are we saying about it?
Okay.
Elva, that it's okay?
But it's not like irrational.
Okay, very good. Yeah, irrational means crazy, right? And rational means sane. Maybe that could be one possibility. Rational means sane and irrational means crazy. It doesn't have to be just sane. Rational could just mean that it's well thought out. You know, it's logical, it's planned, it's orderly. Whereas irrational, again, is crazy or confused or not thinking or not planned. So is that the way we basically use the words? Has anyone ever called you irrational? That'd be an insult, right? It'd be very insulting if someone actually called you irrational. Whereas, has anyone ever called you rational? Like, oh, you're a very rational person. You think through things, right? All right, well, those two words, as we use them in society, has nothing to do with what it means in mathematics. It means totally different things. So when we use the words rational and irrational in a math class, what do we mean? Oh, this is no good. So what does rational mean in a math class? What does irrational mean in a math class? And to tell you the truth, you might even enjoy writing this down. I'm going to put a few things up here on the board. So anyone have any thoughts? What rational means or what irrational means in a math class? Yeah, Brandon?
So like rational is like a kind of like ratio, like you try to have like a, you need to define ratio and irrational, like not really. Yeah,
okay, well, first of all, that's really great, okay? In math class, rational, it should be pronounced ratio-null, okay? Because it's talking about a ratio. And in fact, if we really wanted to be good about it, what I would do is go back about, I don't know, 500 years and show up at the math meeting where they use the word rational and say, no, 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 just use the word fractional. That would have been much better because that's what we actually mean. A rational number is a number that is a ratio, which really just means it's a fraction. So what are some rational numbers? Well, it could be the number 2/3 or 1/5 or -7/2. All of those are rational numbers because they are the ratio of two integers, and it can be positive or negative. There's quite a few other rational numbers you could think of. For instance, the number 5. Is the number 5 a fraction?
Yeah. It's over 1.
You can put it over 1 and then it becomes a fraction. So even whole numbers are rational because technically they can be turned into a fraction over 1. What about the number -10? Is that rational?
Yeah.
Yeah, you can just put that over 1 as well. So that's also still a rational number. What about the number 0? Is that rational? Technically, you could put that over 1 as well. You know, you can put anything over 1, right? Anything at all can be put over 1. So a rational number is really a rational number, which is just a fractional number of two integers. So if you can write the number as a fraction of two whole numbers, then you're good to go. What you can't do, you would not do, like, say, 2.3 over 4. Okay, that would not be rational. Not at least the way it's written, because it has to be the ratio of two whole numbers, okay? And so maybe say that, ratio of two whole numbers. Of two whole numbers. So 2.3 over 4 doesn't count because 2.3 is not a whole number, but I could just rewrite that. I could multiply the top and bottom by 10, and then I would get 23 over 40, and now that is rational. Okay, because it's the ratio of two whole numbers. Likewise, what about the number √4? Is the square root of 4 rational?
Yeah.
Yes.
Can I rewrite it as the ratio of two whole numbers? Yes, I can, because the square root of 4 is simply 2, and 2 is really 2 over 1. So there's a whole lot of numbers in the universe that are considered rational. And all you have to be able to do is just write it as the fraction of two whole numbers. So that gives us a whole lot of square roots, right? Like the square root of 9, how do I write that as a rational number? It'd be 3 over 1, because the root 9 is really 3, and that's really 3 over 1. Okay, so that's a huge class of numbers, folks. And we use the word rational to describe that. Again, it would have been great if we just called those fractional. But see, back in the day, they didn't really use the word fraction. They always used the word ratio. So here we are stuck using the vocabulary of people who've been dead for hundreds of years, and that's just how it goes. Okay, so what is irrational? Brandon already got us started on that. It's irrational. What does the prefix ir mean?
Eat.
What does it say?
I just said eat.
Eat?
No, eat. The E.
Oh, E.
That word from that, isn't it? A number from it, like a letter. The letter E or something like that.
Oh gosh, I have no idea. I mean, what does the prefix mean?
I don't know.
Oh, I'm not sure. I'm not familiar with that. So what does ear mean? Not. Yeah, are there any other words that use ear as a prefix?
Irresponsible.
Yeah, irresponsible. So you've got responsible and irresponsible, rational and irrational. Any others? Ooh, irreplaceable. I like that one, Sarah. You're replaceable versus you're irreplaceable. That sounds much better. Okay, so irrational means not fractional. It means I cannot write it as the fraction of two whole numbers. It cannot be done. Now you might say, geez, what numbers can't be written as the fraction of two whole numbers? But there's a ton of numbers that can't be written as the fraction of two numbers, such as the square root of 2. The square root of 2, famously, historically, was the first irrational number ever found by ancient mathematicians in ancient Greece, maybe around 300 BC, 400 BC, by Pythagoras and his group of cronies. Root 2 cannot be written as the ratio of two whole numbers. It cannot be done. No matter how hard you look to find two whole numbers that you can divide to exactly equal the square root of 2, it cannot be done. So root 2 is irrational. It cannot be written as the fraction of two whole numbers. It's a really good proof, and I think there's even a TED video about it. So if you're curious later, go home and watch the TED video about the irrationality of numbers, or just look up irrationality of root 2, and it'll walk you through the proof. So the proof is cool, but also a really neat story. Because, you know, what is this called? It's like an apocryphal story. It's a story that no one really knows if it's true. But a mathematician one day came to Pythagoras and said, uh-oh, I don't think every number in the universe is rational, which up until that point, they thought every number in the universe could be expressed as a fraction. And this mathematician came along and said, I have a proof that the square root of 2 cannot be written as a fraction. And he showed them the proof, and they were all convinced. But then they were terrified that their whole life philosophy, that all numbers were rational, would crumble if the news got out. So as the story goes, they took that guy out to sea and drowned him so that he wouldn't spread the word that there were numbers that could not be written as a fraction of two whole numbers. Anyway, crazy story, but that's the story they tell. Okay, so root 2 is irrational. So is root 3, so is root 5, so is root 6, so is root 7, so is root 8, so is root 10. Which roots am I writing down? Or better yet, which roots did I skip? I skipped the square root of 4 because root 4 is really 2, which is 2 over 1, and root 4 is rational. I skipped the square root of 9 because the square root of 9 is really 3, which is 3 over 1, which is rational. So all the rest of the roots, that's the square root of a number that's not a perfect square, those are all irrational. They cannot be written as a fraction of two whole numbers. The other group of numbers that are irrational, well, there's a lot of numbers, but pi is also famously one of those. Pi is not a rational number. So there are no two whole numbers that you can divide to exactly equal pi. All right. Well, I'm just excited to share with you kind of this theory about rational and irrational numbers and how we use that distinction. Kind of goes beyond what we're actually doing in this unit, but I find it very interesting. One other thought about rational and irrational numbers. A rational number, if you look at its decimal, it either stops or repeats. So consider 1/2. That's a rational number. The decimal stops, 0.5. Done. Or consider the number 1/3. The decimal for 1/3 repeats, 0.3, 3, 3, 3, 3, etc. So rational numbers, the decimals stop or repeat. So what does that tell you about irrational numbers? What do their decimals do? Yeah, they don't stop, so they keep going forever, and they don't repeat, meaning there's no recognizable pattern within them. So irrational numbers, decimals continue infinitely without repetition. So for instance, pi is 3 point, I have to sing it in order to remember it. In high school, we always sang it to happy birthday. So in 3.1415, 926, 535, 897, 932, 384, 62. Okay, well, that's what we would sing to each other on their birthdays in high school. We could do that too, you know, if anybody was interested. It'd be very fun. So anyway, do you see any pattern in pi so far? Are there any repetitions, or is it, you know, starting to repeat over and over? No. I mean, even 1/7, if you look at 1/7, remember how I said nobody cares about 7? Well, that decimal goes 142,857, 142,857, 142,857. So, you know, decimal repetitions can be quite long. This decimal repetition has 6 decimals. You might say, well, maybe pi does repeat. Maybe if you just go out far enough, you'll eventually reach some sort of huge repeating chunk. But no, that has been proven that that is not true. Pi has no repetition. It's not going to repeat on itself. It will just continue going on forever without any recognizable repetition. Okay, well, folks, that's a little overview of the difference between rational and irrational numbers and what that really means in a math class as opposed to sane and crazy, right? The way we would normally use those words. Okay, all that said, how do you simplify a fraction? And I'll give you a fraction here as an example. How would you simplify the fraction, let's say 8/12? John? You could divide both of them by 4, right? That'd be the technical procedure. I would write divide by 4, and then I'd be left with 2/3. How do you know that you're done simplifying? You can't simplify it anymore, but how do you know you can't?
If there's not a number that goes in.
Yeah, there's not a number that goes into 2 and 3. So John said divide both by 4, and that's true. What if you had kind of done this instead, divide them both by 2? Then I would have had 4/6. But yeah, but now you can keep going. You could, both of those are still divisible by another number, so you could do it again. So that's the classic fraction simplification technique, right? You just go through your mind thinking about what number goes into both of them, and then you divide it out of both of them. Now that's how we usually simplify fractions. There's another way to do it, and I'd like to demonstrate it to you real quick. Here's 8/12 again. Instead of dividing a number out of both, we could write the prime factorization of both numbers, right? 8 is really 2 times 2 times 2, so I'll write that out, 2 times 2 times 2. And 12, if you do the factor tree and write the prime factorization, is really 2 times 2 times 3. Now that I have it written out like that, as a product, notice it's a product, it's a multiplication problem, not an addition problem. It has to be a multiplication problem. Now what can I do? You get to cross things out, right? And that's super fun. You get to cross things out. Whatever you have on top and bottom, you get to cross out. So I can cross out those 2's, I can cross out those 2, and of course, there's our answer, 2/3. Now, I don't know a lot of people who simplify fractions this way, right? Normally, we do the other technique where you say 8/12 and then divide them both by 4, and then you get 2/3. So even though this is the common way people simplify fractions, this is what we'll be doing in this unit, is we'll take a given fraction, we'll factor the top and factor the bottom, just like we have been doing with our factoring techniques. And then you can cross out anything you have on top and bottom. Okay, so that's 2 different fraction techniques for simplification. We'll be focusing on this technique up here. Okay, what can you do anytime you have the same term? The same terms on top and bottom of a fraction, we just said, you can cancel them. Anytime you have the same term on top and bottom, you can cancel. But let's just be very clear about that. In order to cancel a term from the top and bottom, the top and the bottom have to be multiplication problems. So in this example, the entire top was a product, a multiplication problem, and the entire bottom was a multiplication problem. Only if that's true, that it's all multiplication, are you allowed to cancel. What if instead it was 2 plus 2 plus 2 and 2 plus 2 plus 3? Could I cancel now? No. Yeah, I mean, maybe your gut instinct is to say no, but I'm curious, why no? Why is that maybe something that we think is obvious? Like, well, yeah, you can cancel these out, but you can't cancel these out. Why? Is it just a rule immemorial that we have memorized? Why doesn't it work?
2 plus 2 plus 2 would be 6.
Yeah, 2 plus 2 plus 2 is 6. I like where you're going there. And 2 plus 2 plus 3 is 7. And 6/7, that's the actual value of this thing, right? For sure, that's the actual value. And what if I came along and went like that? Is 2/3 equal to 6/7? Definitely not. The decimals don't match. They're not the same at all. So for sure, you cannot cancel if it's addition. Which, another example, let's say you had 2 times 2 times 2, and then on bottom, 2 times 2 plus 3. So, yes, we go.
Because if you like separate them into like similar problems, 2 divided by 2 is 1, 2 divided by 2 is 1. So they kind of like, it just cancels itself out.
Yeah, absolutely. And that's another way, a nice way of saying it is that this 2/2 is really 1. And this 2/2 is really 1. And so 2/3 times 1 is still just 2/3. Yeah, and that's a great way to think about it. And that's actually my last bullet point up there. Okay, so this one, can you cancel it too? No. Because after all, I have here multiplication problem, and I have a multiplication problem. So could I go ahead and cancel these 2's with each other? Now you still have this addition symbol. Addition symbols ruin everything, right? As soon as you have a single addition sign in either the numerator or the denominator, you cannot cancel things out. You just can't. Now, as a side note, that's okay if it's binomials. Like what if I had x plus 3 times x plus 7 times x plus 5, and then on bottom, I had x plus 4 and x plus 7 and x plus 8. Now can I cancel anything? This I can't, because remember, this is a multiplication problem. I've got something times something times something over something times something times something. These are genuine multiplication problems, and now I can cancel out my x plus 7. Even though there's plus signs there, those plus signs are wrapped inside of binomials, and that's safe. So you can cancel these x plus 7s because the plus sign is inside of parentheses. That might feel like a very arbitrary distinction, like, oh, I can't do it if it's like, let's say this. You're telling me I cannot cancel the 7s, and that's true, you cannot cancel those 7s. But as soon as you wrap it inside of a parenthesis, then you can cancel a parenthetical term completely, and that's true. You can cancel a parenthetical term, but you can't just cancel a random thing that's being added or subtracted. Okay, so that's that question. What can you do anytime you have the same terms on top and bottom? And then finally, how many ways can you rewrite the number 1 as a fraction? What's that, Blake?
Infinite.
Like, name a couple.
2 over 2.
Yeah, 1 is 2 over 2, or
3 over 3.
3 over 3, right? The obvious one, 1 over 1. So we've got 1 over 1, 2 over 2, 3 over 3. What else could I put here?
A trillion over a trillion.
Yeah, it could be a trillion over a trillion. I'll just write the word instead of writing it out. What else could it be?
Any number that's divided by itself.
Yeah, any number divided by itself. But it goes beyond numbers. Like, for instance, I could write root 2 over root 2. Now, is this number rational?
It's rational.
It's rational because it goes to
Because you
1.
have to multiply
Yeah.
by.
Yeah, this is a bit of a trick question. Root 2 is irrational. Root 2 is irrational. But root 2 over root 2 is really 1, and 1 is rational. So that's tricky. You always have to look to see if you can simplify it before you decide if something's rational or irrational. So this as a whole is rational because it equals 1. Could I also write down x over x? Is that equal to 1? Yeah, what about x plus 3 over x plus 3? Is that equal to 1? Yeah, that's also equal to 1. So you can rewrite 1 in infinitely many different ways, right? So long as you just put something over itself, it's equal to 1. Okay, well, wonderful, folks. Let's get started. So today, we're starting chapter 7, and that will kind of straddle spring break. I know everyone's pretty sad about spring break. We have to take a whole week off. I know you're bummed about that. I am too. I'd much rather be here. Do you guys want to have class anyway? I could ask special permission to keep this classroom open during spring break, and we could still come in. Well, just think about it. You let me know if that's what you want to do. So we're doing chapter 7, roughly 1 section per day. Today is kind of an introduction day, so we might not even start 7-1, but that's okay. We'll still finish everything. I'm almost done grading your tests. I'll give those back to you on Thursday, and I'll post the grades before. Today's Tuesday? Yeah, I'll have everything done by Thursday. All right, and so a joke. I haven't told you either of these jokes yet, have I?
Mm-hmm.
Okay. What do you call a bear without teeth? What do you call a bear without teeth? A gummy bear. All right. So, folks, we're going to begin chapter 7, and chapter 7 is about rational expressions. Rational expressions. And so just to give an example of that, a rational expression could be like x squared plus 7x plus 12 over x squared plus 6x plus 9. Okay, that's a rational expression. Notice I'm not saying it's a rational number because a rational number would just be like 2 over 3. This is an expression because it has variables. So what we're going to look at for the whole rest of this chapter is expressions and eventually equations where you have some sort of factorable trinomial in the numerator and some sort of factorable trinomial in the denominator, and then you would factor them and simplify. So just as a for instance, x squared plus 7x plus 12 would be x plus 3x plus 4. And then in the denominator, I have x squared plus 6x plus 9, which is x plus 3x plus 3. And then what could we do? We can cancel out the 3's, those x plus 3's. And then my final answer would be x plus 4 over x plus 3. There's nothing else that can be done right there. That's simplified. I can't simplify any more than that. It's kind of like if I started with the number, again, 8/12, it's some sort of a rational expression, and then I want to go through and simplify and get down to 2/3. This is the algebraic equivalent. So I started with a fraction that could be simplified, so I factored it, and then I simplified it. That's what we'll be doing in this chapter, is rational expressions. That said, going forward, we assume that you can do all this in stride. Right? That going forward, you're just like, boom, 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 I can factor, no problem. Like that's just one quick step in a longer process. So whereas in chapter 6, factoring itself felt like the long process that we were doing, now in chapter 7, it's just assumed that you can factor. All right? So you're still practicing factoring, you'll still be doing a lot of factoring, but that's no longer what we're focusing on. Right now, I'm assuming that you feel pretty good about factoring, and we're going to not necessarily show all the steps. Like for instance, you'll notice that to get from here to here, I just went ahead and factored them. Did I show my factor table? Not necessarily, not if you don't need to, right? So if you don't need to show a factor table in order to factor an expression, then go for it. But if it's a tricky one, you should still show your work. Like if I had something like 2x squared plus, I don't know, 7x plus 3 all over. Well, I don't want to continue with an example. The point is, if you need to have a factor table and show your work, do it. If not, if you can do it in your head, then that's okay. All right, so like I said, going forward, I assume that you feel pretty good about factoring and you're prepared to bust out those techniques at any point in the solving of a problem. Furthermore, that we all remember the main theme of the previous unit, which is what does it mean to factor a trinomial? So what does it mean to factor a trinomial? Yeah, turn it from an addition problem into a multiplication problem. And why do we want to factor? Why do we want to turn it into a multiplication problem? Well, there's nothing canceled this here. But why bother turning it from an addition problem to a multiplication problem?
So we can solve using a zero product.
So you can solve using the zero product rule because something times something equals 0 means that either this is 0 or this is 0. And then what do we mean by standard form? Why is this thing in standard form? Oh, that's a typo. That should be a C. But yeah, what is standard form? When we say standard form, that means take your equation and set it equal to 0. And why do we set it equal to 0? So that you can use the zero product rule. So all these things kind of go together. We take addition problems, turn them into multiplication problems, and we make sure it's set equal to 0 so that you can do the zero product rule. And then finally, anytime you solve for x, what did you just find? Like let's say that I took this problem, x squared plus 7x plus 4, and I factor it into x plus 3, x plus 4. And then I solve it using the zero product rule, and I say x equals -3 and x equals -4. What do those numbers mean? That has two meanings. What are these numbers? They are coordinates. Specifically, they are the x-intercepts. Right? Those are the x-intercepts of a parabola. So yeah, that's one interpretation. Those numbers are the x-intercepts. What else are they? They are the numbers that you can plug into the original equation to make it true. Right? So that's the two meanings behind what we do every time we solve an equation, right? Anytime you solve an equation and you get down to x equals, that means that those numbers represent the x-intercepts of the graph, if you happen to graph it, and it means that those are the numbers that you can plug into the equation to make it true. So I say all that because these are the skills that we now assume that you have, and this is the philosophy that I assume you know. We're going for it. And I'm happy to review this whenever. If you have questions about it, please come see me. But these are the core skills, really the core skills for the whole rest of the class. That you can factor, and that you know why we turn addition problems into multiplication problems so you can set them equal to 0, so that you can use the zero product rule, so that you can find the x-intercepts and find the numbers that plug in to make the equation true. All right, that's the bedrock philosophy of what we're doing. All right, so here we begin. Chapter 7, rational equations. What is a rational equation? Now, given all that, everything we've just said, what's a rational equation?
A ratio of 200.
A sane equation. Yeah, a ratio of what?
200.
Well, more than, now it's an equation, so not just a rational number. A rational number would be like 2 over 3. But a rational equation, what would I need? I would need variables, variables and a fraction and an equal sign and hopefully a 0. So when we say what's a rational equation, this would be a rational equation. Now, rational equations come in lots of shapes and forms. It doesn't have to be that it's already equal to 0. It could be that it's equal to 5. And then you'd have to do a little work to rearrange this so that it is equal to 0. It could also be that it's not quite so nasty. It could be something as simple as x plus 5 over x minus 7 equals 2. That's a rational equation right there. It doesn't have to be as bad as that even. It could simply be 1 over x equals 10. That's a rational equation. So what's kind of the key thing that makes a rational equation a rational equation? What do you absolutely need? Well, you could be whole numbers, it could be fractions, it could be decimals.
Variable.
You need variables, of course. It's an equation, so you need a variable and an equal sign. But to make it a rational equation as opposed to anything else, like for instance, is y equals mx plus b a rational equation? Rational means fractional. Is there a fraction in here? No, this is not a rational equation right here. What about a quadratic, ax squared plus bx plus c? Is that a rational equation? No, that's not a fraction. There's no fraction. What do you need to have a fraction? Yeah, you need a fraction, right? You need some sort of a fraction. And more importantly, what you need are variables in the denominator. That's what you really need, is variables in the denominator. So that's my second question. What makes something a rational equation versus a non-rational equation? You need variables in the denominator. So 1 over x equals 10, that's a rational equation because there's a variable in the denominator. Whereas x over 5 equals 10, that's not a rational equation at all. Why is that not a rational equation? Yeah, because there's no x in the denominator, right? This is really just 1/5 x equals 10. And 1/5 x equals 10, I could rewrite that differently. That's 1/5 x equals 10, which is really 0 equals negative 1/5 x plus 10. And this right here is just a linear equation. That's mx plus b. So in order to be a rational equation, you absolutely need to have a fraction. And in that fraction, there has to be a variable in the denominator. So that's what we're studying for the rest of this chapter, is equations that have a fraction and the denominator must have a variable. All right, so everyone take a look at this sheet right here. This will be a pretty quick exercise for you, especially the front side. And I think I'm going to sit this over here so I can write on it. Oh, goody. This will be a very quick exercise for you. I would basically just like you to go on down the page and cancel whatever you can. Anytime you see something on top and bottom, you get to cancel it. So the 7x minus 8s cancel. The 5x squared and the 5x squared cancels. The 8 and the 8 cancels. And what are we left with? There's x plus 8. That simplified quite a bit. Yeah, that's it. That simplified quite a bit. In fact, what looked like a rational equation, in fact, once it simplified, wasn't even rational at all. This is just a linear equation, mx plus b. Right? That's really 1 over 1 x plus b, so that's really mx plus b. So even though this thing looks terribly nasty, if you were to graph it, it would just be a straight line. Right? So sometimes something looks rational, but once it simplifies, it's not rational at all. So let's try another one. What cancels out from here? Jackie? What cancels out?
P plus 4 and minus 2.
Yeah, the p plus 4, the p minus 2. And so all we have left is 5 over p plus 10. Is that rational? Yeah, because there's what? There's a variable in the denominator. If you end up with a variable in the denominator, you're definitely a rational expression. By the way, folks, like the p plus 4, that's technically in a parenthesis, right? And the p minus 2, that's technically in a parenthesis. Because we're multiplying, I should really call that out a little more specifically. Let's look at that problem again. We have this equation, or this fraction, being multiplied by this fraction. And so in the numerator, we really just have 5 times p minus 2 times p plus 4. And then in the denominator, we have p plus 10, p plus 4, p minus 2. You might have to put parentheses around some of these terms to more clearly see why you're allowed to cancel them out. So how about number 3? What do we get to cancel in number 3, John?
I have a question.
Oh, yeah, go ahead.
The 5 and the 10, you can't do anything with those, like reduce them or anything.
Ah, great question, John. Folks, what do you think? Are we allowed to reduce the 5 and the 10?
No.
We cannot, because of the addition symbol.
Okay.
P plus 10, even though that's as a unit, that's a unit, but still you can't simplify the 5 with the 10 because you have a plus sign.
Okay.
John, had it been 5 over P times 10, then the answer would have been yes.
Oh, okay.
Then you could have canceled or simplified the 5 with the 10. But because it's a plus sign, you cannot. Great question. Thank you for asking it. Okay, how about this next one? What can you cancel out of here, Nathan?
2x plus 3.
You can cancel 2x plus 3s.
Pair of 8s.
You have a pair of 8s.
That's it.
Right, so at that point, we're down to 10 over 8 times x minus 2. Is there anything else we can do? We can actually simplify the 10 and the 8 because we do have a multiplication problem in the denominator. We've got 8 times the x minus 2. So that is multiplication, and if you wrap the 8 in parentheses, it might make it more obvious. So now you can simplify the 10 with the 8. And so what goes into both 10 and 8? 2. So that would become 5 over 4x minus 2. And now you're done. You're all done simplifying. And that is a rational equation. Why? Because there's an x in the denominator. Yeah. Okay, how about the next one? What all can you cancel out? Jessica? What all can you cancel? The p minus 8s. Yeah, the p plus 8s. And I guess that's it. So that's p minus 1 over 2. And is that technically a rational expression? Technically, no. Really, that's just p minus 1 over 2. If you rewrite that, that's p over 2, which is really 1/2 p minus 1/2. And that's just a straight line mx plus b. So whereas it looked like a rational expression in the beginning, what it simplifies down to is just a line. And so if you graphed it, you would see a line. How about these last two, 5 and 6? Everybody go and just try those on your own. Go through, cancel, cancel, cancel. And again, folks, it might be helpful to wrap anything in parentheses that's not already in parentheses. Like this p plus 7, that's in parentheses. And this 5 minus n, that's in parentheses. Yeah. Well, that's a good question. No, it's not obviously the same, is it? Yeah, that last one is tricky, isn't it? Okay, let's do these together. What can you cancel out of number 5? Rob?
N plus 2.
The what? I'm sorry, number 5.
Oh, 5. Oh, I'm sorry. P plus 7.
You can cancel P plus 7s,
P minus 7.
P minus 7s,
P plus 2.
P plus 2s. What are you left with?
10 p squared.
It's just 10p squared. That's not a rational equation anymore. In fact, it's a parabola. If you graph this one, you would see a parabola. Not just this. If you put this into a graphing calculator, you would see a parabola. So it has a whole lot of extra terms, and we'll see later what those terms mean. But essentially, this graph is simply a parabola. Okay, now how about this one? This one was tricky. What can cancel, Carla?
N plus 2
The n plus 2's cancel.
and N plus 4.
N plus 4's cancel. Now, can you cancel n minus 5 and 5 minus n?
No.
They're not the same. They're technically not the same. And to convince yourself they're not the same, look at n minus 5, look at 5 minus n, and let's just go ahead and say that let n equal 10. Right? If n is 10, then 10 minus 5 is 5, whereas 5 minus 10 is negative 5. So do those expressions have the same value? No, they're different. So we can't cancel them. We can't cancel them yet. Now, what would I have to do to reverse the sign on those, to change them into n minus 5? I don't know how to do what you just suggested.
Or just change the sign.
We do want to change the sign, don't we? Don't we wish that there was a negative 1 out front? Because if there were a negative 1 out front, what could we do? We could distribute it, and that would become negative 5 plus n, which is really n minus 5. And then the n minus 5 would be the same, right? But do I have a negative 1 out front?
No.
No, I don't. Could I put a negative 1 out front? Just for funsies, could I put a negative 1 out in front?
You have to do it to the top.
I would have to do it to the top too. Right, exactly right. If you want to, you can go ahead and multiply the whole thing by negative 1 over negative 1. Why am I allowed to multiply the whole thing by negative 1 over negative 1? What is negative 1 over negative 1?
1.
This is just 1, right? Negative 1 over negative 1 is just another way of writing 1. And am I allowed to multiply an expression times 1? Yeah, I am. I can take any number in the universe, like the number 10, and if I multiply it times 1, what do I get? 10. So you're always allowed to multiply anything times 1. That's a freebie. And as we've already said, there's infinitely many ways to rewrite the number 1. And so if I wanted to, I could take this expression, multiply top and bottom by negative 1. So let's do it. What do we have at this point? The top is negative 1 times 4n squared. Let me write it in order. The top now is negative 1 times n minus 5 times 4n squared. Right, that would be my top. Whereas the bottom now, what's negative 1 times 5 minus n? I'll write it down once. But then I'm going to do scratch work somewhere else to show what it is. Negative 1 times 5 minus n. If you distribute, that's negative 5 plus n. And then if I just write those terms backwards, that's n minus 5. So now this is negative 1 times n minus 5 times 4n squared all over n minus 5. Now that was, that was some kung fu, wasn't it? That was a little bit of like Harry Potter style kung fu on a mathematical expression. But now that I did multiply top and bottom by negative 1, which I'm allowed to do because it's just equal to 1, now what can I do? Now I can cancel out the n minus 5. And you're left with negative 1 over times 4n squared. And that's what you're left with. Now I realize that one was a little tricky. You might say, oh no, Mr. G, are we going to see things like that? The answer is yes. Because once you're dealing with a rational expression, it opens the door to all sorts of new things you're allowed to do. Because you can always multiply top and bottom by the same number, and that's a legit move. Yeah, Rob.
So if we had a question like this on the exam and people had answered it both ways, would they both be right?
What's both ways?
Well, like the negative 4n. So some people did it with the negative 1, and then some people just left it as the original.
So you're saying, what if you leave it like this?
Yeah.
Like you're saying, can you leave it like that?
Right.
Unfortunately, that would not be simplified.
Okay.
Yeah, because one skill we're going to learn in this unit is that you can easily change the order of a binomial by just multiplying it by negative 1.
Okay.
Yeah, so that's something that we're going to practice. Okay, well, very nice, folks. So what do we learn from this page? That if you start with a fairly nasty-looking rational expression, you can simplify it quite a bit. You can simplify it quite a bit. So now flip it over to the backside. Are we, oops, backside. There we go. Oh, I wish I could see those. Are we ready to cancel things from the top and bottom yet? Not quite. So what is this? X squared minus 4x minus 5 over, wait, what is it?
It's the same top and bottom.
Oh, it's the exact same. Oh, okay. So do we have the exact same thing on top and bottom? Check it out. Wrap it in parentheses. Do we have the same thing on top and bottom?
Yes.
Yeah, so that actually just completely cancels out. We're left with 1 over 1, which is just 1. We didn't even have to factor anything. Like the fact is, I could have factored that into x minus 5 times x plus 1 over x minus 5 and x plus 1. But even if I had factored it, what would I have done? Just canceled them anyway and still gotten 1. Right? So you can factor out, you can cancel an entire trinomial so long as you have the same trinomial on top and bottom. How about this next one? B squared plus 5b minus 50 all over b squared minus 7b plus 10. Did I write those down correctly? Yeah. Okay. Well, these are addition problems. So we can't cancel anything yet. What do we have to do? Yeah, we have to change both of them into a multiplication problem. we have to factor both of them. So
X minus 5 plus X is 10.
the first one would be what? B plus 10, B minus 5? We'll go slowly at first because, you know, we're now kind of accelerating the process on factoring. You could still go ahead and take that numerator and come over here and say, okay, here's my factor table, negative 50. That's 1 and 50 and 2 and 25 and 5 and 10. And I want two numbers whose difference is 5. So that's definitely the 5 and 10. But I need it to be a positive 10 and a negative 5. So yes, the numerator is this. What about the denominator? What multiplies to make 10 and adds to make negative 7? Yeah, 2 and 5, specifically negative 2 and negative 5. So now that's B minus 2 and B minus 5. So we factored the top and the bottom. And then what can you do? Yeah, cross out the B minus 5s, and you're left with B plus 10 over B minus 2. Is that a rational expression?
Yeah.
Yeah, because why? Because there's a variable in the denominator. Yeah. And then we're done. There's no more simplifying on that one. And John, why can't you simplify the 10 and the 2? Yeah, because there's addition going on. So you can't simplify the 10 with the 2. All right, well, very nice, folks. How about this next one? Can we factor the top? Can we factor the bottom? What multiplies to make 30 that adds to make 11? That's 5 and 6, so that's going to be P plus 6, P plus 5. And then what about the bottom? What multiplies to make 10 that adds to make 3?
Plus 5 and minus 2.
Yeah, plus 5 and minus 2. P plus 5, P minus 2. Now, folks, I'm not saying that you have to do all this factoring in your head, right? You can still show all the work that you've ever shown. You can still write down a factor table. You can still brainstorm. But for the sake of class time, the factoring component is a component that we simply do as a matter of course so that we can move on to the good part, which is canceling out the P plus 5s. And so we're left with P plus 6 over P minus 2. And so yes, this is a genuine rational expression. Okay, go ahead and try the last one, number 10. Try that out on your own. Go ahead and factor it in whatever way makes you feel most comfortable. You can try doing it in your head. You can show the factor tables on your paper. Go ahead and factor the top and bottom. So who factored the numerator? What did you get? Oscar, what did you get for the numerator?
Negative 9, positive 2.
Yeah, V minus 9, V plus 2. And then who factored the denominator? What did you get? April? For the denominator, how did it factor? Okay, well that's fine. Who has it factored? Sino?
Oh, X plus 10, X plus 9.
For the bottom?
Wait, number 10?
Yeah, number 7.
Oh, it's V minus 9, V minus 9.
Yeah, V minus 9 and V minus 7. Okay, there we go. So once you factor the top and the bottom, then you get to cancel out the terms of the V minus 9 and the V minus 9. And your final answer is just V plus 2 over V minus 7. Okay. So we started with this activity just so you can see how we're utilizing our previous skills of factoring within the context of a rational expression, which is a fraction, so you can cancel anything in the top and the bottom. We now have to ask the question, what does any of this even mean? Who cares? Why are we looking at rational expressions? What do they even look like if you make a graph? And what are the characteristics of those graphs? And how do we work with them? And what do they even mean? So we're done with that one. Everyone now please take a look at this next page I gave you. It says properties of rational functions. And I'd like to start off by going to my favorite graphing calculator, Desmos. All right. And I need to move my projector back. So, as a class, what we have done together, we know the graph of two different functions. We know lines and we know parabolas. Those are the two objects that we've dealt with in this class. Now, is that fine? Yeah, everybody can see that. So, a line, like 2x plus 3. You know, pretty basic graph. It's just a line, and you can trace along the line and see all the different coordinates along the line. You could find the y-intercept. So there's the y-intercept at 0, 3. You could find the x at -1.5, 0. And what else could we find? The y-intercept, the x-intercept. Talk about the slope. Anyway, that's a line. It's the most basic graph. What about a parabola? Let's say that I had the parabola, I'm going to do x squared plus 2x and then minus 8. There we go. So here's our parabola. And what can we find there? We can find the x-intercept right here. There's an x-intercept. Here's another x-intercept over here. And here's a y-intercept all the way down there. You guys all see that in the back there? So when we look at a graph, we can talk about x-intercepts. We can talk about the y-intercept. And in the case of a parabola, what else can we talk about? What feature is this called, the point at the bottom? That would be called the minimum, just the minimum. So that'd be called the minimum. Whereas if I turned that whole parabola upside down, then you would also be able to talk about the what? The x-intercepts, the y-intercepts, and the maximum. So these are all just different features, right, of graphs that we can talk about. Does a line have a minimum or a maximum? No, I mean, a line just keeps going forever. There's no minimum or maximum. There was a y-intercept and an x-intercept. So what are these new creatures then? What do these new graphs look like? I gave us an example here, and it's x squared plus 2x minus 3 equals x squared minus 2x minus 15. So I just want to graph that real quick. Let me see here. So you can all see where I got this graph from that I put on your page, which is x squared x minus 15. All right, folks, what does that look like? And I'll even zoom out a little bit so you, where's my, hold on, there we go. There we go. What does this shape look like? I'm going to zoom out. What does it look like? I'm going to zoom in. Say that again, what?
They get all the negative y terms and the positive x and x. Meaning like they get the positive x side and then the negative of x.
Maybe. I kind of see what you're saying there. What generally does it look like? For instance, if I graphed a line and I said, what does that graph look like? You'd say it looks like a line. Whereas if I graphed a parabola and I graphed it, you would say a parabola looks like a, like how would you just generally characterize a parabola? It looks like a U, right? So what does this look like? A curve? If I zoom out far enough, what does it look like? It looks like one big plus sign, doesn't it? If I zoom out far enough, it's just one great big plus sign. It's only once I zoom in that you realize something funny is happening in the middle. Because right now, doesn't it just look like a big plus sign? One big vertical line, one big horizontal line. But as I zoom in, you say, ah, there's something clever going on right in there. What's happening right in there? Like if I covered that, just pretend that I've covered it, would it still look like a big plus sign?
Yeah.
With a horizontal line and a vertical line? And you wouldn't have really known or guessed that, whoop, this part connects over to here, and then this part connects over to here. That's kind of funny. So it's like a big plus sign, except for the fact that these two connect up and these two connect up. How else would you characterize it? After all, a straight line is just one line. A parabola is just one U. How many pieces does this graph have? It's technically two pieces. That's kind of strange. There's two pieces to this graph. You've got the piece over here, and then you've got the piece over here. Isn't that strange? A rational function has a graph that consists of two pieces. That's really strange. They don't connect. They don't touch. They don't intersect. All right, well, what else can we say about what this thing looks like? We haven't talked too much about asymptotes, but are there any asymptotes here? Yeah, there are two asymptotes. Where's one asymptote? Is it the vertical one? And I'll even go ahead and graph it. It appears that the vertical asymptote is where? If I were to graph a vertical line right now, it looks like the vertical asymptote is at 5. Does that seem correct? I drew in a blue line there so you could see the vertical asymptote. That's the vertical asymptote right there. So this part over here approaches and gets very close to the blue asymptote. Does it ever touch? Never. That's what an asymptote does. It gets closer and closer and closer, but never touches. Likewise over here, it gets closer and closer and closer. Does it ever touch? No. So we have a vertical asymptote. And where's the location of that vertical asymptote? At 5. Okay. Is there a horizontal asymptote? I'm just going to take a guess here about where that asymptote is. I think the asymptote is at y equals 1. Does my guess appear to be correct? Does this part come down and approach that green line but never touch? Yes. Yeah. And then does this piece over here come up and approach the green line but never touch? Yeah. So it appears as though we have a horizontal asymptote, and it appears as though we have a vertical asymptote. Now, what do the horizontal and vertical asymptote shape, what do they make? An actual big plus sign, right? The vertical and horizontal asymptotes are actually making a plus sign. And therefore, what is our graph doing? Our graph is hugging that asymptotic plus sign, right? So we've got two asymptotes making a plus sign, and this piece of the graph comes in and kind of misses the corner and then goes back up. And then this part over here comes in and then misses the corner and then shoots down. So if you zoom out far enough, both our graph and the plus sign become the same thing. They look like they're the same plus. But in fact, they're not the same because the red curve has this very interesting feature in the middle where it avoids the intersection of those two asymptotes. Okay, there's one other feature here that we haven't pointed out yet. Now, if I scroll along this curve, can everyone see that? I'm moving along, I'm moving along. Oh, first of all, there's the x-intercept, and there's the y-intercept. And as I keep going along, is there a coordinate everywhere along this red line? Yeah, it sure seems as though there is. No, hold on a second. However, what happened at exactly, oh my gosh. Sorry, I'm trying to, what the heck? Oh, there's a hole at 3. Okay, here we go. Look at that. What on earth is this? Hold on, there. What's that? What would you characterize that little spot on the graph? It's a, is there a point right there?
Undefined.
It's undefined. Sorry, it's so tough to keep my mouse on it. If you were graphing a number line, what would you call that? Like, you know how we shade number lines? We say things like x is greater than 3. And so you go to 3, you put an open circle, and then you shade to the right. This is an open circle. Have we done inequalities in here? Maybe we really didn't. Okay. Well, that's an open circle. Technically, that's a hole. We're not saying that this inequality is made true by that point. There's a hole right there. And so look at this graph. What happens right there at 3? there's a hole. That's very strange. It appears as though this graph skips over the value of x equals -3. There's not actually a coordinate there. That's very curious indeed. So we have some mysteries here. 1 second, Oscar. We have some mysteries here, okay? First is, what is this shape? You know, right now we're calling it kind of like a curvy plus sign, but it's made up of 2 components, right? Furthermore, we have asymptotes. We have a vertical asymptote and a horizontal asymptote. And next, there appear to be holes in the graph. Holes where the graph doesn't even have a value. So this rational expression thing is pretty unique. It is a very unique creature, and this is what we're studying for the next month or so. Okay, so I think I'll stop right there. My phone just went off, so we'll take a break. Oscar.
Do you have an equality that shade the graph too?
Yeah. When you do inequalities, you shade. And so the open circle is a spot that you haven't shaded. And so in this graph, what we're saying is that there is no value right there, meaning you didn't shade that part of the graph. Okay, folks, this is a good spot to take a break. The time is 9:02. Let's all start again at 9:12.
Doesn't seem like what time you get up? Get up.
At 7.
This class?
Oh, yeah.
1 class a day? I get out at 2 and then
C-note.
I'll
Do your friends ever call you C-note?
no.
Are you familiar with the phrase C-note? I think a C-note is a $100 bill. Is that correct?
Yeah.
Yeah, a C-note. I don't know why it's called a C-note though. Is it because C is a Roman numeral for 100?
I have no idea.
I mean, we refer to a $100 bill as a C-note. And so I was just thinking that your friends might be like, hey, C-note, how's it going?
I don't even know what
Oh no? Well, here, I'm gonna double check because I don't know why it's called a C-note. 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 It's a slang term for a $100 bill. The C refers to the Roman numeral for 100, which was printed on $100 bills. I had no idea that it was actually printed on a $100 bill. If I had a $100 bill on me, I would just go ahead and look at it. I wonder if there's a picture. Where's the letter C? I don't see a letter C.
maybe you can see when you put it on the right sun.
Oh, when you hold it up to the light?
Yeah.
I'm gonna look. Where is the letter C on the $100 bill?
Oh, it's in the back.
Well, I don't see anything. Maybe it's just something they used to do and they don't anymore. Oh,
Oh,
no.
I didn't even knew that.
You what?
I didn't even knew what C-note. Never heard of it.
Oh, I only ever hear it like in rap songs or like, I don't know. When do people use the word C-note? Am I just making this up? You guys heard of C-note, right?
Heard it. I heard it in a really random way.
Oh, really? Okay.
On this old TV show that I used to watch when I was like 9 called Recess. It
Hmm.
was a cartoon.
Oh, okay.
Not heard of it.
Love that cartoon.
Yeah. Do you remember that they were saying that though? Because I totally remember them talking about.
Not that I remember.
See.
Well, I don't know. Anyways, whenever I think your name, I almost call you C-Note.
Oh, they're making fun of me, like.
No. I think that would be a compliment.
Oh no, my friends like see or no, no.
Oh, C or no.
Yeah.
C or no. That's fine.
No, I feel like I remember like I don't really remember, but I remember like a specific episode where they like found $100 bill I think and they called it like a crisp C-Note.
A crisp C-Note.
Yeah.
Not like those terrible, crumpled up, wrinkly C-Notes.
Okay, how are you?
Do you watch movies? Like a lot.
No, sometimes.
I also hear maybe a bit more. The Korean.
Be better before.
I know.
That is never
Yeah, like, I used to like,
Don't tell me when. I'll probably end up like myself.
It's gonna rain today. It's gonna work today too. What are you watching? Okay.
Thanks.
I like when girls play baseball. But I don't like it. I want to get 100%. I have an exam this week again.
I mean, he's made a tan, I'm not gonna
I want to drop it. Oh, that's when the teacher to drop me the albums.
All right, folks. Everyone back? Let me shout into the hallway real quick. Come on back, folks. All right. So, folks, we're talking about rational functions. And since rational functions are not incredibly common, they're not like linear equations, y equals mx plus b. They're not like parabolas, x squared. It's a whole new creature. So this is kind of like a first date, right? We're getting to know this rational function person. Like, who are they? What's their favorite color? Do they like long walks on the beach? Like, who is this person? So I want to share with you the most basic rational function there is, which is simply the equation 1 over x. 1 over x is the most basic function that satisfies the definition of a rational function. What does this function have that satisfies the definition of a rational function? It's a fraction, and it has a variable in the denominator, right? It can't get any easier than that. It's a rational expression because it's a fraction, and it's got an x in the denominator. So this is the easiest, most simple rational expression you can have. And notice the shape. What is the shape? If I zoom out far enough, what does it look like? A big plus sign, but something wonky happens in the middle there where it's approaching the origin, but it curves away and doesn't actually reach. And so you got the two pieces, the piece up there and the piece down here. So I wish I could make this bigger for you, but I'm going to take the 1 over x, and I'm just going to manipulate it a little bit to show you how you can change the graph a little bit. So let's take a look at the 1. What if I make the 1, hold on, let me zoom in. There, what if I make the 1 negative? There. What happens if I make it negative? Yeah, it changes directions. Now, technically, it's tough to see this. It's flipping upside down. So watch that component right up there, up top, and it goes down below, right? So that part went down, and then what did this part down below do? Go up. So technically, it flipped upside down. I could see how someone would make the argument that it flips right and left. Could you also make the argument that it's flipping right and left? Whoops, oops. Could you make the argument? Yeah, I mean, relatively speaking, I suppose you could say that it's either flipping up and down or that it's flipping left and right. That's really in the eye of the beholder, isn't it? Okay, so that's what happens if you make it negative. What if I start changing my x? What if I put a number on x, like 5? Or better yet, 6, or 7, or 9, or 10, or 20, 30, 40. What's happening? Yeah, it's getting really close to the origin. You could even say it's like pinching its way there. So now you can barely see the gap anymore unless I zoom in. And what will you see if I zoom in?
Wherever cross.
The same picture. Will it what?
Would it ever like touch the?
It's a good question, folks. You answer that. Will it ever touch?
No.
No. As much as I keep going and then I zoom in again, right? And then I keep making that number in the denominator bigger again, and then I keep zooming in again, what's going to happen? It's never really going to reach. It will pinch and pinch and pinch, getting closer and closer, but it's not actually going to get there. Okay, so this is back to my normal graph. Let me get rid of all the zeros. Okay, what else could I do? I could add a number to the x. So let's say I add 1, or add 2, or 3, or 4, or 5. Where is it going? Bye. So it's kind of marching its way over, oh no, until, all right, it's all the way, I moved it all the way over that way, right? So let me move it back. Now it's back to the origin. Now what if I subtract a number? If I start subtracting 1, then 2, then 3, then 4. So what would we call this? If I'm moving it left and right. It's just a horizontal transformation. I'm just taking the object and I'm moving it left and right. Just like you could take a parabola and move it left and right. Well, what else could I do? Instead of adding or subtracting a number to x in the denominator, what if I add or subtract a number to the entire rational expression? If I add 1, 2, 3, 4, what's happening to it? Goodbye. I just shifted it up. Now what happens if I bring it back down and instead of adding 1, I subtract 1? And then 2, 3, 4. And goodbye. Yeah, so clearly we can do lots of transformations to this. I could do it all at once. I could make the top negative, which flips it upside down. I could move it to the left 4 places, and then I could move it up 3 places. And so now I have a whole new graph, but it's still the same shape, right? It's still the essential same basic shape, which is the new shape that we're studying. So this thing is called a rational expression. It's a rational graph, and that's what it looks like. The characteristics we've discussed so far is that you have an asymptote, a vertical asymptote, a horizontal asymptote, and you might even have a what? A hole. You could even have a hole. Now, just for fun, just to be suggestive here, I would like to add a hole to my graph at the value of 8. So everybody look right here. Is there currently a hole at 8? Let me get, oh, there we go. Is there a hole there? No. But now watch what I'm going to do. I'm going to take my graph, and I'm going to, or my graph, I'm going to multiply it times x minus 8 divided by x minus 8. Now, technically, what is x minus 8 divided by x minus 8? It's equal to 1. Did my graph change at all? No. However, now look at where the number 8 is. I just put a hole there. Now, first of all, that's kind of cool. I can put a hole anywhere I like. And how did I put a hole there?
By multiplying times 1.
By multiplying times 1, by putting in the expression x minus 8 over x minus 8. Now, technically, x minus 8 over x minus 8 is just equal to 1. So it didn't change the overall graph. But am I now allowed to put 8 into this function? What would happen if I plug 8 into it? What's 8 minus 8? 0 over 8 minus 8? 0? What's 0 divided by 0? What's 0 divided by 0? Undefined. So you're able to put in a hole anywhere you like by putting in these terms that are the same on top and bottom, and that creates a hole. Okay, we're going to explore this more. I'm really just kind of, it's like an overview. It's like I'm just showing you lots of features, and we'll get into more detail. But I think that just about covers what a rational function looks like and the features. Poles, asymptotes, x-intercepts, y-intercepts, the fact that it's two components, and the fact that you can manipulate it, move it left and right, up and down, flip it upside down. These are all the things you can do with a rational function. Doesn't it sound like a good friend that you'd want to go on vacation with? Right? It's a pretty good function. It's got a lot of versatility and a lot of interesting features. A lot more interesting than a line, right? Who wants to go on vacation with a line? Lame. I want to go on a vacation with a rational function. That sounds like a good time. All right, back to our sheet. I know, I'm crazy. Back to our sheet. So consider the rational function. There it is. X squared plus 2x minus 3 all over x squared minus 2x minus 15. Is it a rational expression? Yes, why? Variables in the denominator, right? And there's my graph. You can already see it. You can see that I have a hole there. I've got a vertical asymptote. I've got a horizontal asymptote. Let's say hello to this function. The graph has shown it right. Trace in the vertical asymptote at x equals 5 with a dashed line. I better not write on this projector. Bring it back over so I can trace on this just like you're going to trace on it. Let's go ahead and, there we go. Let's go ahead and draw on this graph. So where's our vertical asymptote? Here. There's my vertical asymptote. I don't know that we have already reviewed the equation for a vertical line, but the equation for a vertical line is x equals the x-intercept. And so since this vertical line crosses the x-intercept at 5, the equation of that vertical asymptote is x equals 5. So there's our vertical asymptote. It also says, well, actually it doesn't say it, but let's go ahead and trace in the horizontal asymptote as well. There's a horizontal asymptote, which is there. And that horizontal line, any horizontal line is given by the equation y equals the y-intercept. And so the equation of that horizontal line, since it goes through at 1, is just y equals 1. So far we can see the vertical asymptote at x equals 5. X equals 5 kind of names where on the x-axis the vertical asymptote is. So there's a vertical asymptote cutting through the x-axis at 5. There's a horizontal asymptote cutting through the y-axis at 1. Okay? Notice that's just where the asymptote cuts through. We're not saying that those are x-intercepts and y-intercepts of the graph, right? The actual graph does not cut through the x-axis at 5. That's just where the vertical asymptote is. And the actual graph does not cross through the y-axis at 1. That's just where the horizontal axis, the horizontal asymptote is. Okay, so tracing the vertical asymptote at x equals 5. I forgot to write here to trace in the horizontal asymptote, but there it is. And then notice the hole at x equals -3. Go ahead and just get in there, make that hole in your own pencil, and then call it a hole. Now, just to clarify, no matter how fast no matter how much of a hurry you're in, you never refer to an asymptote. Well, no, okay, well, I'm just trying to make a joke. If you were to write down asymptote and hole, don't abbreviate as that, okay? Don't do that. It's not the proper way. If you wanted to, you might have to write asymp hole, okay? That would be better, that'd be better, but let's not abbreviate it that way. Okay, so what else? Question. Why does the graph have the properties shown? So we've just kind of gotten to know this thing. We know there's lots of properties. There's two components. There's a vertical asymptote. There's a horizontal asymptote. There's a hole. But why does it have these properties? Okay. What is it about a fraction? What is it about variables in the denominator that cause these properties? That's what we'd like to ask. So did I put that on your page? I don't think I did. No. Yeah, maybe write that in. Why the hole? Why the asymptote? And fundamentally, the answer to these questions is because there are variables in the denominator what might happen. Because there are variables in the denominator, so for instance, in this one, it's x squared minus 2x minus 15. What might happen if I plug in just the right value of x. For instance, what happens if I plug in the value of x of 5? What happens if I let x equal 5? Well, go ahead and plug it in. What happens to the denominator if x is 5? 5 squared, I'm gonna write it out. 5 squared is 25, minus 2 times 5 is 10, minus the 15. What's our denominator?
0.
0. Well, now that's a problem. Can you divide by 0? You're not allowed to divide by 0. It's undefined. Right? Now what about the numerator? Was that okay? 5 squared is 25, plus 2 times 5 is 10, minus 3. That's 35, minus 3 is 32. Numerator was just fine. The numerator actually equaled some number, but the denominator went to 0. And that 0 causes problems. You could say it causes problems. You could say it wreaks havoc. Let's just be a little dramatic. You can't divide by 0. That's undefined. And so why do rational functions have these interesting properties of wholes and asymptotes? Well, because there are variables in the denominator, which is our definition of a rational function, you might accidentally, plug in an x value that causes the denominator to equal 0. Right? So we kind of stumbled into this whole thing like, oh, sure, rational numbers. That's a fraction of two numbers. And a rational expression, that means there's variables in the denominator. Well, as soon as you put a variable in the denominator, you're allowing for the possibility that the denominator could equal 0. And if the denominator equals 0, that's undefined. And so anytime the denominator equals 0, okay, anytime you plug in a number that makes the denominator equal 0, you either just created an asymptote or a hole. You either just created an asymptote or a hole. So in this case, what did I create by letting x equal 5? What did I create? An asymptote. I created the asymptote by letting x equals 5. Well, that is, there is an asymptote there because by plugging 5 in, it created a 0 in the denominator. Okay, let's try one more. What if I let x equal -3? What happens then? I'm going to show my work again, but down below. What happens if I let x equal -3? If I plug in the denominator now, -3 squared is 9. Minus 2 times -3 is plus 6. And minus 15, 9 plus 6 minus 15? Still 0. Right? So if you plug in the right value for x and you end up dividing by 0, you either just created a hole or an asymptote. But what about the numerator now? If I plug in -3, -3 squared is 9. 2 times -3 is minus 6. Minus 3. And what's 9 minus 6 minus 3? 0. Whoa, a double whammy. Right? This was 32 divided by 0, which is undefined. But this is 0 even 0, which is like even worse. So what was what? 32 over 0 was the asymptote. And what was the 0 over 0? The whole. So already we can say a couple of things. We can say a rational expression has variables in the denominator. Because it has a variable in the denominator, you might plug in a value that causes the denominator to equal 0. And if the expression becomes a number over 0, that's an asymptote. But if it makes the expression equal 0 over 0, that's a hole. So we've already kind of identified something. That we can identify the properties of a vertical asymptote and a hole just by finding out when the denominator is equal to 0. And if the denominator equals 0, it's either a hole or an asymptote. If the numerator is a number, that's an asymptote. But if the numerator is a 0, that's a hole. And that's something we can take with us for the rest of this chapter. Oscar.
So you always start with the denominator first?
Yep, denominator is of primary importance. You start by looking at the denominator. Yep, we always look at the denominator first. Because, why? Why do we look at the denominator first?
Because let's see if it's
Well, for a variety of reasons. Yeah, it's irrational. Yes, there's variables in the denominator. But what's the big no-no? What are you not allowed to do? Divide by 0. So the denominator is important first and foremost because you want to know when you're going to accidentally divide by 0. Because if you do divide by 0, that either just caused an asymptote or a hole. Okay, let's keep going. That was just kind of an introduction. Yes, the denominator is very important because there's variables down there, and depending on what number you plug in, you could divide by 0. And if you divide by 0, your graph will have a hole or an asymptote. So there are 3 things we're going to do. We're going to find the domain of this function. We're going to find any holes, and we're going to find any asymptotes. So let's start with find the domain. You'll have to take these notes. I have them on the screen, but you write them down. The domain is defined to be all allowable inputs. All allowable inputs. All the numbers that you're allowed to plug in so that you can actually calculate a real number. That's a very short definition of domain. If you were on Cash Cab and they were like, hey, what's the domain of a function? You could say, oh, that's all allowable inputs. And you would win the money because that's the correct definition. But if you wanted to be more specific, like you're on Who Wants to Be a Millionaire, and if they said, what's the domain? You would say, okay, the domain of a function is all the numbers in the universe except those inputs that would cause you to divide by 0 or square root a negative, right? Because you're not allowed to divide by 0 or square root a negative. So yes, domain is just all the numbers that you're allowed to plug into a function that your calculator would actually calculate a value for you. You know, your calculator wouldn't say error, undefined. The domain is all the numbers that you can actually calculate an answer. So we already know the 2 exceptions, right? For this particular function, what are the only 2 numbers we can't plug in?
0. Oh, 5 and -3?
Yeah, 5 and -3. We already found them. So we already know. The domain is all the numbers in the universe except for 5, which causes an asymptote, and -3, which causes a hole. So in this particular case, we can already say the domain is everything except x equals 5 and 3, 5 and -3. Okay, that's just a shorthand. I'm just writing it in English to recap what we already know. We do have a more formal way of saying it. So let's go about the process of identifying the domain of this function. What would we do? It says, thus, our job is to find out when the denominator is equal to 0. So to do this, we usually have to factor. So notice what I just took. I just took the denominator only. What's our function again? It's x squared, what's on top?
X squared
Plus 2x minus 3. So I've got this function, x squared plus 2x minus 3. But the denominator is of primary importance. And I'm saying, well, the domain is any number in the universe except where the denominator is going to equal 0. So what you would do is you would take the denominator, set it equal to 0, factor it using your normal factoring skills, use the 0 product rule to find out those are the 2 values that will make the denominator equal 0. So that just confirms what we already knew using the skills that we just learned in chapter 6. You take a trinomial, you factor it, use the 0 product rule, you solve. So since plugging 5 or -3 into the function will make the denominator equal 0, we will exclude the values of 5 and -3 from our domain. And notice in the graph that x equals 5 is the asymptote and x equals -3 is the whole. So thus, the domain of the function is all real numbers except 5 and -3. That's what it would look like if you wrote it out in English. The domain is all real numbers except for 5 and -3. However, we can write it using set notation. So everyone try writing it with me here. Just write it again. The domain would be the set of all numbers x such that x just isn't equal to 5 or -3. That's called set notation. It's how you'd write the domain in set notation. Honestly, I don't think that we'll use that very much. I think we'll be much more likely to write interval notation. And so we write it in interval notation like this. Now, my goodness, what is that? Remember, we're talking about x values. So we're talking about the x-axis. And what we're saying is on the x-axis, you can't do the number 5, and you can't do the number -3, but you can use every other number. So that's what our number line would look like of the allowable x values. You can plug any number to the left of -3 into that function. You can plug any number between -3 and 5 into that function. And you can plug any number bigger than 5 into that function. But you can't plug in -3 or 5. And so using interval notation, which I'm just now realizing that I don't think we've ever done interval notation in this class, have we? Geez, that's a problem. Okay, we'll have to review interval notation. But the way this would work is, since this is going to -infinity, and that's going up to +infinity, you have 3 different intervals. You've got the interval from -infinity to -3. You've got the interval from -3 to 5. And you have the interval from 5 to infinity. And so you write it out as the first interval first, from -infinity to -3. The U stands for union, which means or, from -3 to 5, which is -3 to 5. Or, again, the U stands for union, which means or, from 5 to infinity. I will start us off with a warm-up in next class using interval notation. So if that doesn't make a ton of sense right now, that's okay. We'll review it in the next class. The key thing to note is we've just found out that we're not allowed to plug 5 or -3 into this function because it would make the denominator equal 0. And the graphical result of that is that you see a vertical asymptote or a hole. Okay. So the domain is all numbers in the universe except for 5 and -3. Okay, turn it over. Right, we're going on the back. Okay, 2, find any holes. So how do we find a hole?
We make the bottom equation zero and see if it has a negative.
To see if it has a negative?
Well, I was thinking how we did it earlier that we solved.
Yeah, well, how we did it earlier was we took our function, and when we plugged in 5, didn't it equal 32 over 0? Whereas when we plugged in -3, it equaled 0 over 0. And we're saying anytime it's a number over 0, it's an asymptote. And anytime it's 0 over 0, it's a hole. But there's an easier way to know if something is a hole or an asymptote. So let's take a look. In order to find holes and asymptotes in a rational function, you have to first completely factor the original function. So notice this is the function we started with, but now I already factored it for you. Okay? Does everyone agree that I factored this correctly?
Yes.
X squared plus 2x minus 3 becomes x plus 3x minus 1. Is that correct? Yeah. And x squared minus 2x minus 15, is that x plus 3 x minus 5? Yeah, I think I did it correctly. So there's our factoring. Now, once a rational function is factored, we are allowed to what? Cancel any binomial terms that are in both the numerator and the denominator. So go ahead. What do you get to cancel? You get to cancel the x plus 3's. By definition, the whole is represented by the binomial that you just canceled out. So any binomial that you cancel from the top and bottom, you just found a whole. So that's the term x plus 3 represents the whole. And if x plus 3 represents the whole, what's the actual whole value? Remember, we're wanting this not to equal 0. So we're asking us the question, when is that equal to 0? When is x plus 3 equal to 0? When x equals -3. So where's the actual whole? At -3. So let's be clear here. The binomial x plus 3 represents the whole. X equals -3 is the actual whole. Okay? So when you have a rational expression and you factor it and you cancel anything, those terms that you just canceled represent a hole in the graph. But keep in mind that binomial x plus 3 merely represents the whole. You still have to set that thing equal to 0 and solve for x. And so x equals -3 is the actual whole value. That's where the actual whole is. And looking at your graph, that is where the hole is. You'll notice the hole is at -3, not at +3. At +3, there is an actual value. There's no hole there. So x plus 3 represents the hole, but x equals -3 is the actual hole. Okay, so that's how you find a hole. Where are the holes? Any binomial term that cancels from the top and bottom, that's a whole. The other way to recognize it is if you plug the actual value in and you get 0 over 0, that also tells you it's a whole. So there's two ways to know that you're looking at a whole. What's the last section? Find the asymptotes. By definition, the asymptote is given by any binomials in the denominator that you cannot cancel from the denominator. So is that what we were left with? After we canceled the x plus 3 and the x plus 3, is that what we were left with?
Yeah.
Yeah. So after canceling the x plus 3's from the top and bottom, this is what we're left with. We're stuck with the x minus 5 in the bottom. That term, the uncanceled term, represents the asymptote. So anything you're stuck with, I was not able to cancel out the x minus 5. It remains. So the x minus 5 represents the asymptote, and you still have to take that, set it equal to 0 to find out when would that term equal 0. And so the actual asymptote is at x equals 5. So where are the asymptotes? Any binomial term that's left in the denominator after you do all of your canceling. The other way to recognize an asymptote is that if you plug that number in and you get a number over 0, that's an asymptote. Okay, so we have multiple tools at our disposal, right? A whole is any binomials that canceled, any binomials that cancel, whereas the asymptote is any binomials that remain. All right? So we've learned a lot. We now understand a few properties, just a few properties of a rational function. What properties do we understand so far? What features of a graph? The asymptotes and the wholes. And they're both caused by division by 0. Yeah, asymptotes and wholes are caused by division by 0. They're very different features, aren't they? I mean, an asymptote is very different from a whole. And yet they're both caused by dividing by 0. Okay, so in conclusion, when looking at a rational function, so there's my original, there it is factored, I canceled those out, and now I have my final. The domain, let's just summarize here. The domain is all real numbers except those inputs that make the denominator equal to 0. Thus, the domain is everything except for 5 and negative 3. You can plug anything else in. The wholes are given by the binomials that are canceled. And so our whole was located at negative 3. And then the asymptotes are given by the binomials that are not canceled. And so our asymptote was at x equals 5. Okay, so when we look at a rational function, we're now able to explain and understand. Oh, I should make mine look like this one. We're now able to explain and understand where the vertical asymptote is and where a whole is. But we have not yet talked about where is the x-intercept and where is the y-intercept. And what else have we not talked about? We know the vertical asymptote, we know the whole, we don't know the x or y-intercept, and we also don't know yet the horizontal asymptote. So there's still a little bit more for us to understand about rational functions. So let's turn the page over. And part 2 is going beyond the denominator. All right, the denominator was of primary importance because you don't want to divide by 0. Divided by 0 causes wholes and asymptotes. And it determines your domain. But we also need to go beyond the denominator. We probably won't finish this in 5 minutes, but let's just see where we get. So there's more to a rational function than just the denominator. For instance, there's also the numerator. What does that do? You know, it's just off the top of our head. Is there anything important about the numerator? I mean, is the numerator allowed to equal 0?
Yeah.
Numerator is allowed to equal 0. You're allowed to have a fraction, like you're allowed to have f of x equals 0 over 5. You type that into your calculator, it's just 0. It's perfectly fine for a fraction to equal 0. And in fact, when it does equal 0, just for instance, let's say I plug in 5 and let's say I plug in 2 and it equals 0. That means my input is 2, my output is 0. And in fact, that tells me the x-intercept. So it's more than fine for the numerator to equal 0, because that means the whole expression equals 0, which tells me I just found the x-intercept. So that's helpful, because we still want to find the x-intercept, the y-intercept, and the horizontal asymptote. So in fact, yeah, when the numerator is 0, we just found the x-intercept. Okay, so let's explore the 4 parts of a rational function that tell you about the graph. There are 4 key details about a graph that we can identify just by looking at the function. And I think I already put them in a particular order, didn't I? Yeah, x-intercept, sorry, y-intercept, x-intercept. The y-intercept, the x-intercept, vertical asymptote, and the horizontal asymptote. These are the 4 features, ultimately, that we want to know about. You'll notice I didn't write whole. I suppose whole would be right there with vertical asymptote, because vertical asymptotes and wholes are both found in the same way, by dividing by 0. So these are the 4 features we'd like to find. Everybody look at our graph and notice that we already know the answers. So where's the x-intercept? Can you see it on your picture?
6,
6, 0. Okay, so the x-intercept is at 6, 0, or in other words, just x equals 6. Where's the y-intercept?
0, -3.
Is it -3? So the y-intercept is at 0, -3, which is x or y equals -3. The vertical asymptote in the whole we already found. We'll just go and write it down real quick. The asymptote was at x equals 5, and the whole was at x equals -3. And where was our horizontal asymptote? Did we already trace it in once? Yeah, it was the line y equals 1. So the horizontal asymptote was at y equals 1. Okay, so what we're about to do is understand how to get this information, the y-intercept, the x-intercept, the vertical asymptote, the horizontal asymptote, how to get this information without looking at the graph. Okay, so we're just going to pretend you're not allowed to look at the graph, you're stuck on an island, you don't have a graphing calculator or Desmos, and all you can do is look right here. That's what we're about to find out. How do you get all this information just by looking at the function? Oh, by the way, I'm so sorry. I changed functions on us. We're no longer looking at the function that we were before, and so I no longer know the location of the asymptotes and wholes because we're not looking at the same thing in the horizontal asymptote chain. I'm so sorry. I totally forgot. We're looking at a new function. Forget the old function. We're talking about something new now. We still did the correct y-intercept and the x-intercept because it's right there on the graph. You can see it. Where's our vertical asymptote, you think? I don't think it's -5 because the line is already touching -5. So where is it more likely? I think it's at -4. So everyone go ahead and trace in your vertical asymptote at x equals -4. And in this particular graph, there is actually no hole, so we're just going to cross that out for now. And where's our horizontal asymptote? It's kind of tough to tell from the drawing, but the vertical asymptote is at, I'm sorry, the horizontal asymptote is at 2. So you can go ahead and just trace that in for now. The horizontal asymptote is at y equals 2. The vertical asymptote is at x equals -4. Okay, so we have all the information. And we got all that information from the graph. But as I said, now our job is to get all the same information just by looking at the function. That's, I don't know what that is about mathematics, but there's always 2 skills, right? One skill is looking at a graph, and the other skill is looking at the function. So it's fairly easy to look at a graph and get all this information. We now want to learn, how do I get this information just from the function? So that's where we'll end today. When you come back, we'll wrap this up, and then we'll start section 7.1. Thank you very much, folks. If anyone has any questions, come on up here and ask. I'm going to my office for office hours, I think. So.